Good morning. We kind of jumped forward in time there because I wasn't sure that video was recording, but it did record well, so I'll add this little part to it. So once you've identified that angle theta is the angle in question, we can find these two sides that I call FG perpendicular. So that's this component of the weight, and FG parallel. And we're interested in a coordinate system that's parallel to the plane of the slope because this is the direction that the object will accelerate in. So really this is the main direction that we're interested in decomposing our vectors into, or directions aligned with that, because that's the direction of acceleration. So the kind of weird thing is the parallel side, we find it using the same trigonometric functions that we found before. So if we look back here, it might be a little easier to see our right angle is here. So this is the opposite side. FG parallel is opposite in that triangle where FG is the hypotenuse. So if FG is the hypotenuse, we're going to use find FG parallel, we'll just say FG parallel over FG. So FG parallel, or the part that it would balance with friction or would work with friction, is equal to FG sine theta. And FG perpendicular is this side that's adjacent to the angle theta, and so we're going to find it using cosine, just in the same way. FG perpendicular over FG. So FG perpendicular is FG cos theta. So this is really easy to see if you have a really well-drawn triangle. So I like to remember that this angle here is the theta, is like kind of an armpit angle. It goes toward the normal force here. Notice that FG parallel is found with FG sine theta, and it does look like it's kind of in an x-axis, and if you use the reference tables, you would actually end up with FG cosine theta. So you just need to be a little careful with these ramp ones. You can't use your regular reference table formula, but you can, of course, always use a nice trigonometric analysis. So let's look at an example problem on the next page, page 41. So Nori is skiing down a hill with a 25-degree slope. From our reference tables, we know that wax skis on snow, the coefficient of kinetic friction for wax skis on snow is 0.05. What is Nori's acceleration down the hill? So we know her mass is 60 kilograms. From that, we know her weight, which is equal to her mass times little g. We're going to round little g to 10. And we know that mu is 0.05. Our free body diagram, this is usually what I recommend you do first. So that's way too dramatic of an example. So let's try that again. Awesome. And then here's our skier. You don't have to draw a really great skier. Mine's pretty decent. And I forgot we actually know theta. Theta is 25 degrees. So let's draw the forces that act on our skier. So we have force of gravity, straight down, 600 newtons. We have normal force perpendicular to the surface, and then we have the force of friction opposing motion. So if I rotate this, like I did before, it's just easier to see how to create the components of this force of gravity. Because we can see really easily that here's theta, here's our right angle, and we need some part of the force of gravity that's parallel to friction or parallel to the ramp, which we just solved to be Fg sine theta. And then we need some component of force of gravity that balances out with the normal force. Fg perpendicular is Fg cos theta. So notice now, like, this vector is actually kind of gone, because what I've done is I've taken it and broken it into its components. So really, this black vector here is kind of redundant. So now that we have all the forces here, and I will have that black vector in here, even though it is redundant because these two are its components, so these two add up to this one. There isn't like an extra one. We can analyze the red direction, which is the y direction, or the direction perpendicular to the ramp. And we can analyze that blue direction, the x direction, or the direction parallel to the ramp, whatever you want to really call it. So in the y direction, we're not like going up off the ramp or the hill or down into the hill. So we're going to say, because a equals 0, Fn equals Fg cos theta. Well, that's nice because we're probably going to need Fn, because if we look at the x direction, we want to find Norrie's acceleration down the hill. So that's in this x direction, or the parallel direction. So we're going to say that F1 plus F2 equals ma, our usual F net equals ma sort of formula, where Fg parallel, or Fg sine theta, is in this positive rightward direction, and the force of friction is in the negative direction, and then that equals the mass times the acceleration. So we need to figure out all these things in order to ultimately get at the acceleration. Well, conveniently we know Fg, we know sine theta, we know Fg, and we know cosine theta, and we could probably find Ff by saying Ff equals mu Fn. So let's just do a little aside here. Ff equals mu Fn. So Ff equals 0.05 times Fg, or 600 cos 25. So I'm going to pause it for a second and do all these calculations, and then I'll come back to you. So all I did was type in 600 cos 25. I got 543.8. So that goes in here, multiplied by mu, and we get a force of friction of 27.2. So 600 sine 25 was also 253.6. So if I take this, which I calculated, and I subtract the force of friction, 27.2, I should get my mass, which was 60 kilograms, times my acceleration. Now there is a little bit of rounding going on because I did call G10, but we're close enough. So 253.6 minus 27.2 is 226.4. We're going to divide that by 60, and we get an acceleration of 3.77 meters. So this is like the hardest problem you'll probably ever see in this class, or maybe even in other future physics classes. So my point in doing this is just to show you that even the hardest problem is really totally doable using the same strategies and procedures that we've done before. So these problem-solving strategies are so valuable because the procedure can be applied to all sorts of different things. So just a brief overview, we drew our free body diagram. We aligned the forces in the direction that acceleration was happening, which was down the hill, and also we aligned the forces perpendicular to the hill, determined the givens, and we used our good old F equals ma or F net equals ma formula to analyze both the parallel to the hill direction and the perpendicular to the hill direction to ultimately get the acceleration. So we'll show you some little more straightforward or chunked problems in class just to find the different components of that weight perpendicular or parallel to the hill. Have a good day.